What's up, smart people? Welcome back to another episode of Simple Harmonic Motion. Today we are down to episode 6. Okay, we actually come really far. Just a few more episodes to go actually. But anyways, okay, what we'll be talking about in this video is we're going to learn how to sketch graphs of acceleration against displacement and velocity against displacement. We have learned how to sketch of acceleration and velocity against time, right? But this time we're going to look at how does the graph look when it's against displacement. We're going to touch a teeny bit on energy because I believe it'll come in handy when I explain things to you and you will understand better. But we will not draw energy graphs in this video. I will put that to the next video because I'm afraid the video will get a bit too long, right? So without further ado, let's get started. Okay, before drawing graphs, I'm gonna explain to you using the spring here. As you can see, I've drawn a spring and there's a few things here, A, V, X. I know you might be wondering what it is. So A is acceleration, V is velocity, X is displacement, KE is potential energy, PE is potential energy. So what I'm gonna do now is I'm gonna explain to you how acceleration, velocity, displacement, KE, PE behaves at each point that I have written them. Basically, at its minimum displacement and maximum displacement, or in other words, maximum amplitude or minimum amplitude. Okay, let's start with displacement, the easiest one. So we know displacement at its equilibrium position is definitely 0, right? Because you are at equilibrium position. Now what about to my right hand side of my equilibrium position? Will it be positive or negative? Actually, before that, I forgot to mention. So this is actually a spring that is moving in this direction. Then after that, it changed direction. It reverses its direction, of course. Then it goes this way. So it will keep oscillating until it restores itself to equilibrium. So this is what the spring is all about. Okay, now going back to my displacement. So as the spring moves to the right of your equilibrium, it has gone here, it's gone to the right this side. What would my displacement be? My displacement would be positive. Because if you remember in the first video that I've mentioned, anything to the right of the equilibrium has a positive displacement, anything to the left of the equilibrium has negative. But you can also set your left hand side to be positive and your right hand side to be negative, as long as you're consistent with your sign. Yep. So we know anything to the right hand side of the equilibrium is now positive displacement. Anything to the left hand side gives you a negative displacement. Okay, we are done with our displacement. Now let's talk about acceleration. So acceleration is related to resultant force, where we have a formula of F net equals to ma. And we have discussed that since the only force involved here is the spring force, or also known as the restoring force, we have negative kx equals to ma, which we have derived, gives you negative omega a equals to negative omega square x. Right? Okay. So now I want you to take a moment to think a bit. If my spring moves further away from my equilibrium, do I need a lot of restoring force to restore myself back to its original position, or do I need a little bit of force? Of course, you need a lot of force. So when you need a lot of force, that means you need a lot of acceleration as well. That means at your maximum displacement, at your maximum amplitude, your acceleration is maximum. Same goes to minimum displacement, because minimum displacement is also means you're furthest away from equilibrium. You need a lot of force as well. So your acceleration is also maximum at your minimum displacement as well. Now what about equilibrium? Easiest way to know your acceleration is at equilibrium is by using this formula. You know your displacement at equilibrium is 0 because you are at equilibrium. So if you sub in 0, you're gonna get A equals to 0. So that means your A is 0 at your equilibrium. Another way to explain this is you are already at equilibrium. You don't need any restoring force. You don't need to restore anything, right? So of course you don't need any acceleration. That is why the acceleration is 0 at equilibrium. Now, the last one here, velocity. What will your velocity be at your maximum displacement? When it moves here, then when it turns, it actually stops. It momentarily stops before reversing its direction. Am I right? So at this point, at a maximum displacement, at your highest amplitude, the velocity is 0. Same goes to your minimum displacement as well. Because when it comes here, it's going to stop for a while. It's going to stop momentarily before reversing direction. Before the spring reverse direction. And at this point, your velocity is 0. Okay. Now, what about your equilibrium? Will your velocity be 0 as well? Or will it be maximum? Your velocity will actually be maximum. Now, I'll explain this in terms of energy a bit, because I believe it's an easier way to understand this. Now, at this point, I said it will momentarily stop before it reverses direction. When it momentarily stops before it reverses direction, your velocity is 0. That means your KE is 0. When your KE is 0, your elastic potential energy at a maximum amplitude or your displacement position will be maximum. Because it's stretch maximum, and at maximum amplitude, your potential energy would be maximum. Remember, energy cannot be destroyed. You can only transform energy or transfer energy, basically interchange of energy, but you cannot be destroyed, right? Cannot be destroyed. So when your kinetic energy at this point is 0, your potential energy is maximum. All the energy is stored as elastic potential energy of the spring. Okay, now after this point, it's going to come to equilibrium. As it moves towards equilibrium, your PE will start to decrease and your KE will start to increase as it's moving towards equilibrium. Why? Because at equilibrium position, your spring is not stretched or compressed. It stores no elastic energy. That's why potential energy is 0 at equilibrium itself. So for it to be 0 at equilibrium itself, you have to slowly decrease as you move towards equilibrium. So at equilibrium, the system's entire energy is kinetic energy at this instant. The mass is like zooming past the center at a maximum speed. So at equilibrium, your kinetic energy is maximum. This one is as you move towards equilibrium, your potential energy slowly decrease, kinetic energy slowly increase, until eventually at equilibrium you reach maximum. Then after that, what happens? You're going to go back to your maximum amplitude. Your kinetic energy will slowly decrease, your PE will increase. Then at maximum amplitude, what happens? Your KE is 0, your PE is maximum because you are stretched. It's at maximum. So this is the reason why your velocity at the x0 displacement, sorry, at equilibrium is actually maximum. It has maximum kinetic energy as the spring passes through the equilibrium and it moves with a maximum velocity. Yep. So this is a brief explanation on how energy works a bit in simple harmonic motion. So yep, that's about it. Also, don't get confused by what I mean here and what I mean here. What my blue line here is saying is the process as it moves towards equilibrium. How's the energy flow going? the PE will slowly decrease, the KE will increase. The moment it reaches equilibrium, it's at maximum kinetic energy and your potential energy is 0. Because once the mass has passed the midpoint of its oscillation, the kinetic energy will slowly decrease, potential energy is slowly increase. All the energy is transferred back to the spring because of elastic potential energy. Then at its now its minimum displacement, your KE is 0, your PE is max. Yeah. So you need to be aware of sometimes what the question is asking. If they're asking as it moves towards the equilibrium, then you will say PE decreases, KE is increasing. But when it's at its equilibrium, your KE is maximum. With that being said, your velocity is maximum and your potential energy, your elastic potential energy is 0. Yeah. In this case, we're talking about elastic potential energy because it's a spring. Okay. Alright. Now, we can start drawing our graphs. That's the main thing, right? Okay, we will start drawing our acceleration against, how am I spelling against displacement? This is one of the easiest graphs to draw. A, we have X. So, we know at equilibrium, A is 0, X is 0. This is your first point. Now, at maximum displacement, what will your acceleration be? So, let's sub in some value inside. So, we know this is the equation. So, let's say, and we know at maximum displacement, it's at maximum acceleration. It has a maximum acceleration. So, I put A max here. Negative omega square is constant, of course. X. At maximum, my X is positive. So, let me put as positive X naught. X naught is my amplitude, highest amplitude, maximum displacement. So I get negative omega square X naught. I want to realize something here. Realize when my displacement is positive, my acceleration is negative. And it's true because remember we said it's always in opposite direction. So our next point would be, okay, let's say this is my X naught and I have a negative acceleration. So we have this point here. Now what about at its minimum displacement? Minimum displacement, you have negative omega square, and since I set the left side of my equilibrium as negative, I would have negative X naught. Again, I'm mentioning my X naught here, I denote it as my maximum displacement, basically my amplitude, highest amplitude or the lowest amplitude here. So I will get, there's no negative really, omega square X naught. Still, I got a negative displacement, I got a positive acceleration, which is true. So negative displacement, my acceleration is positive. I'm going to write it this side so that I can draw that point. Okay, and we get a straight line, which is consistent with our facts, because remember I said acceleration is directly proportional to X, just that they are in opposite direction. And this negative shows that it's a negative gradient, and we did get a negative gradient. So this is how you draw A against displacement graph. Very easy, right? Just sub in inside a formula, you'll actually eventually get your answer. Now, our last graph of the day, V against X. Okay, let's choose a different color. Okay, this color. V against X. Okay, so V against X, there's actually a formula, and the formula is V equals to positive negative omega X naught square minus X square, and X is basically any displacement point of X, any point. So what does this equation mean is This equation is trying to say is velocity at any displacement of x. Any displacement of x. And your x naught is your amplitude, yeah? Your highest max or minimum amplitude. Now I know you might be thinking, where in the world this equation came from, because we've never seen it before, right? All we've been talking is velocity against time, a cosine form of velocity. Now why suddenly there's a square root and there's also plus minus? Okay, so the derivation is not really required in A levels, but I will derive it for you in the next video if you're actually curious on how to get this. It's actually a way. You need to use a bit of differential equation, but not as much as you need for displacement with respect to time equation. But I will show you in the next video. For now, just know that this particular equation exists. Okay? Alright, now let's sub in some values, okay? So we know at the maximum displacement or the minimum displacement, your velocity is 0 because it momentarily stops before it reverses direction. With that being said, our maximum amplitude position is x naught. Negative x naught is our minimum, right? And we know that the velocity is 0 here. So we know these are one of the 2 points we should have in our graphs. The next 2 points is the maximum point, right? Because we have 2 maximum points here. Why? Because first, the spring is probably moving in this direction, then it's going to rotate, reverse, then it's going to keep oscillating, right? So we have 2 maximum points here. So now, where is the maximum point? The maximum point is when it's at its displacement. And at its displacement, we know our x is 0. So let's sub in inside this equation. You would get v equals to positive negative omega square root x naught square minus 0. Because remember I say x is just any point at any displacement. So v equals to positive negative omega square x naught square. You'll get positive negative omega x naught. So this shows your maximum is positive negative omega x naught. So since we have positive and negative, positive here, omega x naught. Place my naught up. And we have a negative omega x naught. So we have 4 points already on our graph. Now I know you might be thinking, how am I supposed to draw this graph? You're gonna get an egg. I'm very sure you're gonna get an egg. So we'll just draw an egg. But make sure it's oopsie. Okay. Okay, did not touch the point. Okay. It's not. I did not touch the point. Okay, wait a minute. Just give me a while. Okay, something like that. You will basically get something like an egg figure of velocity of the graph of velocity against x. So yeah, this is how your velocity against x looks like. Looks like an egg, and your acceleration against x looks basically like a straight line. Yep. So that's about it for today's video. We actually come to the end of it. And just to recap a bit, what did we learn? We learned about which point acceleration is maximum, velocity is maximum, and we also talked about briefly on how the energy works. We'll draw the graph in our next video. I'm not going to draw it here because I'm afraid it's going to be a bit too long, so I'm going to draw it in the next video. But yeah, this is a brief idea about energy and also how to draw graph of acceleration against x and velocity against x. If I straight away jump into the graphs without explaining using this, you might be a bit confused, so I thought it's the best way to explain. So I hope it helps you, and I'll see you in the next one. Bye bye, have a nice day, and remember to stay hydrated, okay?